Okay. Okay. Okay, let us continue to the question number 3 in test 8. Okay. In this problem, in this question, we will discuss about the angular momentum and the principle of conservation of angular momentum. Okay. So far, we have talked about the moment of inertia. Okay, with we have seen that it has a similar property as the inertia of mass in the linear motion, and also we discussed the torque of a force F acting on an object around some reference point. Okay, and we say that the torque change the state of rotation of the object. Now, in this problem, we will discuss what is the state of rotation of the object. Okay. If we compare with the linear motion, we say that the state of motion of an object under linear motion is its momentum. Okay. So similarly, the state of motion of an object with rotation is the angular momentum. Okay. So first, let us see the definition of the angular momentum. Assume that we have an object. Okay. Moving with linear momentum p. Okay. And we want to calculate the angular momentum of this object around a reference point O, and we have the position vector of this object with respect to the reference point O. Okay. We define the angular momentum equal to the cross product or vector product between position vector and linear momentum, like this. Okay. We again use the vector product here to define the angular momentum. Okay. So we can write down the magnitude of the angular momentum is equal to rp sine theta, where theta is the angle between vector r and vector p. Okay, and the direction follow again the right hand rule. Okay, so in this case, consider if we have the vector r point along your forefinger and vector p point out from your palm, like this. We have the direction of the angular momentum along your thumb. Okay, so we have the angular momentum vector point in this direction. Okay, this is a general definition of the angular momentum, but in our case, for the basic physics, we are interested on the special case of motion, that is the motion along a fixed axis. Okay, you have an object move in a circular path, rotate along a fixed axis like this, and you have the position vector r from the axis to the object, and the object move with the linear momentum p. Okay. Since the object moves in a circular path along this axis, so we only have the tangential component of the momentum, okay, because the object cannot move away from the axis. So what we must have is that the position vector and momentum will always perpendicular in this case, okay. So it means that in the case that we are interested, the angle theta will always equal to 90 degree or pi over 2. It means that we will have that the magnitude of the angular momentum is equal to Rp sine pi over 2, and we know that sine pi over 2 is equal to 1, so we have that this is Rp, the product of Rp, or if we write P as a mv, so this is a Rmv, okay. So this is the magnitude of the angular momentum of the object move in a circular path along fixed axis, okay. And also the direction of the angular momentum vector follow right-hand loop. Now let's see this relation. If we put V equal to omega r, okay, omega is the angular speed and r is the radius of the rotation. So we will have that L is equal to r m omega r, or is equal to mr square omega. But mr square is nothing but the moment of inertia of the object allow this fixed axis. So we can write this equal to I omega like this, okay. So we have that in the case of the object move around a fixed axis, the angular momentum is equal to the moment of inertia times the angular speed, okay, like this. Now we can go further, that similar to in the case of the linear momentum, that is, if we have a system of particles, more than one particle, and the force that act on each particle is an internal force, okay, it means that it's a force between the component of the system. It's not come from the third party, okay. We will have what is called the conservation of angular momentum, okay. I will not prove this, but I will use the result of this principle. That is, if there is only internal force in the system, we will have that the angular momentum is a constant, okay. This is very similar to the case of linear momentum. That is, if we have a system of particles, and if the forces on each particle come from another particle, it's an internal force. It's not come from the third party. It comes from the object that not belong to the system. We can say that the momentum, the total momentum of the system is constant, or it will not change in time. In the case of angular momentum, it's the same. That is, if there is no internal force, in fact, we may say that there is no external torque. We have the internal torque only that make the system rotate, okay. We can say that the angular momentum is a constant. Okay, follow this principle, we can solve the problem number 3. The question asks that a horizontal platform in the shape of a circular disc rotates freely in a horizontal plane about a frictionless vertical axle. The platform has a mass m equal to 100 kg and radius r of 2 meters. A student whose mass is 60 kg walks slowly from the rim, from the rim of this toward its center. If the angular speed of the system is 2 radians per second, when the student is at the rim, meaning that this rotates with the angular speed of 2 radians per second when the student is at the rim. What is the angular speed when she reaches point r equal to 0.5 meter, half meter from the center? It means that this student walk from the rim toward the center, and when she is at the distance half of meter from the center, what is the angular speed of the system? During her walk from the rim toward the center, you can see that the corresponding force comes from the force between her feet and the surface of the disc. So it means that we have only the internal force, and this internal force produces only internal torque. So it means that we can use the conservation of angular momentum to calculate this problem. If the state 1 is when the student is at the rim, and the state 2 is when the student is at the distance 0.5 meter from the center, we must have that the angular momentum of the system at the state 1 and at the state 2 are the same. And we know that the angular momentum is equal to I omega. So we have I1 omega 1. I1 is the moment of inertia of the system at the state 1. Omega 1 is the angular speed in the state 1. Is equal to I2 omega 2. And rearrange this relation, we have omega 2 is equal to I1 omega 1 over omega 2. We know omega 1 which equal to 2 radian per second. What we have to do is calculate I1 and I2. And the moment of inertia is the moment of inertia of the system, which means that the moment of inertia of the disc plus moment of inertia of the student. And you can see that moment of inertia of the disc not change between state 1 and state 2. But moment of inertia of the system change because the distance from the center to the student change when she moves from position 1 to position 2. Moment of inertia at the state 1 is the moment of inertia of the disc around its center, so it is a half of mr squared plus moment of inertia of the student, and we assume that the student is act as a particle. So we use mr squared as a moment of inertia of the system when she stands at the rim of the disc. So we have r here is 2 meters. Moment of inertia of the system when the student walk to the position 0.5 meter from the center. Is the moment of inertia of the disc which not change, you can see, plus moment of inertia of the student. Now it's become mr squared. This is a small r, and this r is equal to 0.5 meter. And we know all we want. After you put the numerical value to these two expression and put those values into the expression for omega 2, you can easily calculate the angular speed of the system when the student walk to the second position as 4.1 radian per second. So it means that the answer is D. Okay, so that is all for the test 8.